the last lecture notes, if they're not uploaded, we'll do it today. Just remind me at the end of the class. Okay, cool. Now let's start talking about sorting. Okay, anybody who knows what is sorting? Anyone who knows what is sorting? It's a new topic. It's a new concept. Let's see. Very good, Shadan. Very good. Very good. Oh, a lot of you guys have the correct answer. Very good. Okay, let's try to understand the word sorting. Sorting means arranging data in a specific order. Arranging data in specific order. Right. For example, let's say I have a list of products on Flipkart. Okay, let's assume that this is list of products on Flipkart. Okay, right. Now, generally, you see some options to sort by price. You see some filter options to sort by ratings and so on. Can I see that? Everyone, are you guys able to get this point? Is this making sense? So what we are doing, we are going to start learning sorting. Okay, and what is sorting? Sorting means arranging data in a specific order. A lot of times on e-commerce applications like Flipkart and all, whenever you have a list of products, you see some options like sort by price and sort by ratings. What are these options going to do? These options are eventually just going to do one simple thing. That is, they are going to rearrange the list of products, maybe by increasing order of price, or decreasing order of price, or increasing order of ratings, or decreasing order of rating, or something else, right? This operation is called as sorting. And you have been doing this for quite some time, right? Every time you shop on any e-commerce product, you do sorting, right? So sorting is one of the most fundamental problems. Sorting is one of the most fundamental problems that actually exist in computer science, right? And there are different ways to do sorting, okay? A lot of times people think that sorting means arranging data in increasing order. That's not a correct definition of sorting. Sorting means arranging data in any specific order. Sorting means arranging data in any specific order. And generally, people mean that we are trying to arrange the data in increasing order. But that doesn't make it the definition of sorting. Definition of sorting means arranging data in any specific order. Okay. Now you might be thinking that, okay, now how should we do sorting? As I mentioned, for different scenarios, for different use cases, there are different sorting algorithms available, right? But let's start with the worst possible sorting algorithm. Let's start with the worst possible sorting algorithm. What do I mean when I say worst possible sorting algorithm? This is the sorting algorithm that will take the maximum amount of time to sort any particular piece of data. This is kind of like a no-brainer algorithm in which you do not put any strategy, you do not put any, I would say, special cases, right? And it will just sort the data, but it will take enormous amount of time. And what is that? A lot of people think that there's a very famous algorithm called as bubble sort. A lot of people think that worst possible sorting algorithm is bubble sort, but that is wrong. Let me tell you what is the worst possible sorting algorithm. So what is the meaning of sorting? Meaning of sorting is arranging data in specific order. What is arranging data also called as? Arranging data is also called as permutations, right? Arranging data is also called as permutations. So let's say we have a data like this, 5, 4, 3, 2, 1. Okay, we have data like this, 5, 4, 3, 2, 1. And we want to arrange this data in increasing order. Okay, so you can see very carefully, I'm specifically mentioning what order is the required order, right? Now what I can do is, how about I generate all possible permutations of the data, right? Let's say I generate all possible permutations of the data. If I generate all possible permutations of the data, can you see different permutations will come up? 4, 5, 3, 2, 1, 4, 3, 5, 2, 1, 2, 5, 1, 2, 3, and so on. And one of these permutations is going to be 1, 2, 3, 4, 5. So what I'm going to do is I'll be generating n factorial permutations in the worst case. In worst case, n factorial permutations. And among all of those ones, I generate all of those permutations. Then among all of those permutations, I will check which one of them is arranging the elements in increasing order only. And that will be my final answer. So this is the worst possible sorting algorithm, right? Here we are not taking anything specific. Here we are just going by the definition of sorting. That definition of sorting is arranging data. Arranging data means permutation. So how about we generate all possible permutations of the data, and among all of the possible permutations, we check which one is the desired one. For example, let's say the data is something like this. Let's say the data is like 3, 2, 1. So I'll generate all possible permutations. 3, 2, 1, 3, 1, 2, 2, 3, 1, 2, 1, 3, 1, 2, 3, 1, 3, 2. And among all these possible permutations, this is the only one which is in increasing order. So we will one by one generate the permutation, and we will check whether this permutation is the required one or not. Whether this permutation is required one or not. Whether this permutation is required one or not. I hope this point makes sense. And this actually makes the worst possible sorting algorithm. And what do you think will be the time complexity of the worst possible sorting algorithm in the worst case? You can see that we will be taking, let's say, k amount of time. Let's say we take k amount of time to generate one permutation. And how many total permutations we will get? N factorial. So the total time complexity will be what? Order of k into n factorial, right? And anything multiplied by n factorial is also going to be approximately equal to order of n factorial, right? So you can say that the worst possible sorting algorithm sorts your data in n factorial time. Does that point make sense, guys? Am I making sense or not? Right? A lot of people think that bubble sort, selection sort, these are the worst possible sorting algorithm, but that's not true. That's not true. The worst possible sorting algorithm is the one which generates all possible permutation. People are saying repeat the part of k. I'm saying, let's say, to generate one permutation, we do not know how much time it will take. Let's say it will take some k amount of time. This k can be n, it can be n square, it can be n cube, doesn't matter. Final permutation will be, if k amount of time is taken for one permutation, how many time it will take for n factorial permutation? K into n factorial. Now, whatever is the value of k, if it will get multiplied by such a huge quantity like n factorial, it will be equivalent to n factorial, right? Like, just think about it. N into n factorial is also n factorial. And I will teach you later, once we start with backtracking and everything, that to generate one possible permutation, we need order of n time in the worst possible, like in the worst possible algorithm. Does that one make sense? We do not need to care about the best, but yes, the best will also be around n factorial only. Why? Because at least you need n factorial time because you have to generate n factorial permutations. Can I say that? Right? You need at least n factorial time because if you take constant amount of time to generate one permutation, then also you need to go to every permutation at least, right? Is this point making sense to everybody? Drop a quick yes or no in the chat, guys. Okay. Now let's start talking about some smart algorithms in that case, right? I don't think there's name of this algorithm. You will not find every time name of every algorithm, and name of the algorithm also doesn't matter, to be very honest. You need to know what the algorithm does rather than the name. I guess Bogo sort has some sense of randomness. We are not doing any random possible generations or anything. Got it? Okay, cool. Let's come back. Now we know what is the worst possible sorting algorithm. Now let's start talking about maybe some better ones. Okay. So we'll start with one very interesting sorting algorithm, which is very important as well, because if you continue your journey with data sources and algorithms, you will see occurrences of this algorithm later as well in other topics as well. We're going to talk about selection sort. Okay. What is selection sort, guys? Okay. Let's try to understand it like this. So consider the following. Consider the following scenario. Okay. Let's say, first, we have a collection of numbers. We have a collection of numbers, which is, let's say such that the first half is sorted in increasing order. Let's say we want to figure out the algorithm to sort the data in increasing order. Okay. So what I'm saying is, let's say you have a collection of numbers. You have a bunch of numbers such that the first half, so the first initial part, and I should not even write half, I should say first part is sorted in increasing order, and later part is unsorted. Okay. Later part is unsorted. So what scenario I'm saying? I'm saying something like this. Let's say you are in a situation where this much part is actually sorted. This much part is, let's say, unsorted. Okay. Some initial part is sorted. The remaining part is unsorted. Okay. This is the first scenario. Okay. Then what is the second scenario? Or let's say, what is the second part of the scenario? The second part of the scenario is that the biggest number of the sorted region, is smaller than smallest number of unsorted region. Okay. Okay. Listen to this very carefully. Just assume for a moment that you land up in a scenario. Where initial part of your collection is sorted in increasing order. Later part of your collection is unsorted, and the biggest number of the sorted region is smaller than the smallest number of unsorted region. Let me give you an example like this. Okay. So the example of this scenario can be 1, 2, 4, 5. Okay. And then let's say 10, 13, 8, 6, 12. Okay. Now, can I say that this region is sorted? This region is unsorted. Okay. And if this region is sorted, can I say the largest number or the biggest number of the sorted region will be the last number of the sorted region? So can I say this is the biggest number of sorted region, right? And because this is unsorted, so this unsorted region can have the smallest element anywhere. Let's say this is the smallest element, right? So you can say this is the smallest element of unsorted region. Okay. And can I say that the biggest number 5 is lesser than the smallest number of unsorted region? Can I say that, right? So let's say this is the scenario in front of you. What my question is, figure out how can we expand the sorted region? How can we expand the sorted region and shrink the unsorted? How can we expand the sorted region and shrink the unsorted? How can we do that? Why not we take 1, 2, 4, 5, 10, 13 as sorted? Amit, in the start only I said a word. Consider. आपको कंसीडर करना है सिनेरियो दैट आफ्टर डूइंग सम ऑपरेशंस यू लैंड अप इन अ सिनेरियो लाइक दिस वेयर initial part is sorted, later part is unsorted, biggest number of the sorted region is lesser than the smallest number of unsorted region. You have to figure out how to expand sorted region, how to shrink the unsorted region. You have to assume that you land up in a scenario like this. Then the smallest number will become Sanjeet is saying that, sir, what if you have a 2 here? What if you have a 2 here? Then this hypothesis is wrong, because I'm saying that we will always land up in a situation like this where the biggest number of the sorted region is lesser than the smallest number of unsorted region. We have to abide by this situation. We have to abide by this situation. Okay, so I'm giving you a situation, guys. I'm giving you a scenario. I'm taking you to a path where you have to figure out something. Okay, you are inside a problem statement. Abide by the problem statement. Okay, assume this is the scenario and you have to come out of a solution. How will you do that? Very good, Shruti. Very good. Very good, Jayant. Very good. Makes sense, Vivek. What smallest number, Chandni? Guys, I believe you guys can figure it out. How can I expand the sorted region? I don't think, Bhushan, that will be the optimal one. Compare the element sorted region to smaller. You're missing something, Guru. Okay, let's start talking about it. Now, as I said, we are into this situation, okay? And we have to come out of this situation somehow, okay? How can I do that? The simplest way of expanding the sorted region and shrinking the unsorted region is going to be by just doing one simple thing. What is going to be that one simple thing? What we can do is, in the unsorted region, because we know the division of the region, right? We know the division of the region. So in the unsorted region, how about we find the smallest number of unsorted region. We find the smallest number of unsorted region and put it after the biggest number of sorted region. How about this? That I take the smallest number, I somehow try to find the smallest number of the unsorted region and put it here. So let's say I swap these two. 10 comes here, 6 comes here. Can I say now the sorted region has expanded and the unsorted region has shrinked itself? Right? Let's see this with an example. Let's see this with an example. Okay. So we are into a situation like this. Let's say 9, 6, 2, 1, 4. Okay. Let's say this is our initial array. This is our initial array. When you start this algorithm, can I say the sorted part is empty? There is nothing sorted as of now, right? And this is the unsorted part. This is the unsorted part. And why I'm saying sorted part is empty? Because how do we define the sorted part? We will only get the sorted part if the biggest number of the sorted part is lesser than the smallest number of the unsorted part. But you can see I cannot consider 9 as a sorted part because 9 is not less than 1. Can I say that? So initially, when you start your algorithm, your sorted part is empty and unsorted part is the whole array. And you will see step by step, we are going to expand the sorted part and shrink the unsorted part. Okay, cool. So what is the strategy that I mentioned to expand the sorted part? I'm going to find the minimum element here. Now you have to find the minimum element. Okay. So first step is find minimum element. We will discuss more about finding this minimum element later. Okay. Let's assume for a moment that we know how to do it. Okay. For the moment, just assume that we know how to do it. Okay. So in this region, what is the minimum element? The minimum element is 1. And what did I suggest? You swap the minimum element with the first element of the unsorted region. You swap the minimum element with the first element of unsorted region. See, you want to swap 6 with 10, then only you will put 6 after 5, right? Our agenda is to put 6 after 5. If you want to put 6 after 5, you need to swap 6 with 10. So what I'll do is, I'll swap 4 and 9. The moment I swap 4 and 9, 4 comes here. Sorry, not 4 and 9, my bad. 1 and 9. 1 and 9. 1 and 9. Because 1 is the smallest, right? So we swap 1 and 9. And the moment we swap 1 and 9, this is the situation of the array. And now can I say, this is the sorted region and this is the unsorted region, right? Can I say in one step, I'm able to expand the sorted region and shrink the unsorted region? Again, I will find the minimum element. In the unsorted region. What is the minimum element in unsorted region? Here the minimum element is 2. Okay. Again, what we are going to do? We are going to swap 2 with 6. Okay. So what will happen? 2 comes here. 6 goes here. Right. And now if you carefully try to understand, this is your sorted region. This is your unsorted region. Can I say that? Again, I will repeat the same step. Find the minimum element. What is the minimum element now? 4. We will spend some time, of course, to find the minimum element. But what we are going to do, we are going to swap 4 with 6. Okay. If you swap 4 with 6, what you will get? 1, 2, 4, 9, 6. Sorry, 1, 2, 4, 9, 6. And now if you carefully see, this is the sorted region. This is the unsorted region. Right? Let's do it one more time. Find the minimum element. What is the minimum element here? 6. What will you do? You will swap 6 with 9. 1, 2, 4, 6, and 9. The moment you do this operation up till this point, you will be having only one element left. When you only have one element left, then you can say everything is sorted. You can say now everything is sorted. And can you see, we are able to arrange our data in increasing order. we are able to arrange our data in increasing order, right? This process is called as selection sort. In selection sort, we try to rearrange our data such that we always maintain a partition where initial part is sorted, latter part is unsorted. And the biggest number of the sorted region is lesser than the smallest number of the unsorted region. This is what selection sort is. And I believe the moment I gave you this situation, most of you were able to figure out how you will expand sorted region and how you will shrink unsorted region. And technically, you yourself figured out what is selection sort. I don't have to put a lot of effort into feeding you the algorithm. You yourself figured out that, okay, if this is the situation, that's how we expand the sorted region and that's how we shrink the unsorted region. And you yourself figured out selection sort. How cool is that? Can I say that, everyone? I'll come to time complexity and everything. Adi saying what happened in the first element of the unsorted region smaller than the... Adi, do you think I started with an absolutely unsorted array? Do you think we will land up in a situation what you are mentioning? I don't think so. Guys, did you just figure out that you yourself found out what is selection sort? If you will go to the internet, just FYI, if you go to the internet, for example, and you search for selection sort, of course, our favorite website, you can see they just directly start telling you, okay, take the smallest element, put it to the start. Take the smallest element, put it to the start. No intuition at all. No intuition at all. Vivek, मैं तो कराऊंगा ही ना, कहने की जरूरत क्यों है? But here, intuitively, because I gave you a situation, you yourself figured out, oh, that's how things are expected to be done, right? Yes or no, everybody? This is how you should learn algorithms. Later, in the later part of data structures and algorithms, we will again visit selection sort for more optimization. Okay. But first of all, let's come to the coding part. Okay. Now, before we go to the coding part, this thing is yet to be figured out. How to find a minimum element? Can I say if I want to find the minimum element, can I do linear search? Can I do linear search? For example, let's say 96312. Okay. What I will do is, this is index 0, 1, 2, 3, 4. Okay. I will say minimum element index is equals to 0. Okay. I will assume that this element is the minimum element. And then what I'll do is I'll go to every element one by one. I will check. Is 6 less than the element at index 0? Yes. So definitely 6 is smaller than element at index 0, right? I will update it to index 1. We go to the next index. Is 3 lesser than the element at index 1? Is 3 less than the element at index 1? Yes. So we have found an even smaller element. So we will put the index as 2. Then we go to 1. Is 1 less than the element at the second index? Yes. So what do? We update the index as 3. And we go to index 4. Is 2 less than the element at index 3? No. 2 is not smaller than 1. So 2 cannot update the element at index 3. Hence, we have read all the numbers. And at index 3, we have the smallest element. Can I say that? We read all the numbers, and at index 3, we have the smallest element. And don't you think this is kind of like a linear search approach, where we go to every element and try to check if it is the desired answer or not? That was what linear search was doing. That you go to every element and check if it is the desired answer or not. Here also, we are going to do the same thing. Right? Here also, we are going to do the same thing. Make sense? Now, we know the whole algorithm. What's the time complexity here? Let's try to figure out the time complexity. Let's take one more example. 5, 4, 3, 2, 1. Okay. There are total n elements where n is equals to 5. Okay. In the first iteration, what we are doing? We are going to every element. We are going to all the n elements and checking which one is the smallest. Can I say that? We are going to go to every element and check which one is the smallest. Same thing here we were doing. We were going to every element to check which one is the smallest. And can I say we figured out 1 is the smallest number? Right? You can check 1 is the smallest number. Right? So in the first iteration, we are making n checks, or you can say for getting the first number, we are making n iterations. Can I say that? So in the first iteration, you will take n iterations to find smallest number. Then, the moment you have one element in the unsorted region and n minus one elements in the one element in the sorted region and n minus one element in the unsorted region, the moment you have to find the smallest number again, you do not need to go to n numbers again. You can just check among the n minus one numbers. Can I say that? You can just check between these n minus one numbers, what is the smallest number? So to check between the n minus one numbers to check what is the smallest number, you just need to go to all the n minus one numbers one by one. So can I say in the second iteration, you take n minus one iteration to find the smallest number. Then your sorted region becomes of size 2, unsorted region becomes of size n minus 2, right? So among the n minus 2 numbers, if you have to find the smallest number, how many iterations do you need? N minus 2 iterations. So in the third iteration, you need n minus 2 iterations to find the smallest number, and so on. And so on. You will do this till the time you have one number left. So how many iterations total we did? For the first iteration, we did n iteration. For the second iteration, we did n minus 1 iteration, n minus 2 iterations, n minus 3 iteration, and so on. Up till you have what? 2 elements left, 9 and 6. When you have 2 elements left, you need to check both the numbers to find what is the smallest number, and that's it. And that's it, right? That is it. Let's total it up. Okay. Can I say this is equivalent to sum of first n natural numbers minus 1, because you can see there is no 1, right? If there would have been 1, it would have been sum of the first n natural numbers. Can I say that? Right? It would have been the sum of the first n natural numbers. But this is sum of the first n natural numbers minus 1. So what is the sum of the first n natural numbers? N into n plus 1 by 2 minus 1. Right? Now can you see? Minus 1 is a constant. So we are going to avoid it. This becomes n into n plus 1 by 2. And 1 by 2, this is what? 1 by 2, right? 1 by 2 is also a constant. This becomes n into n plus 1 in the worst case. We are talking about the worst case. And n into n plus 1 is n square plus n. This is a lower degree term. For example, if n is 10 raised to the power 5, this is what? 10 raised to the power 10 plus 10 raised to the power 5. 10 raised to the power 10 plus 10 raised to the power 5 is what? 10 raised to the power 10. So we will avoid the lower degree term as well. We get n square. We get n square. That means in the worst case, the time complexity will be big O of n square. How about that? Is this point making sense, guys? Okay, let me quickly repeat. Okay, let me quickly repeat. So if you want to just quickly repeat the time complexity analysis, I'm saying when you started, then you had to do n iterations to find the smallest number. In the next step, you have to do n minus 1 iterations to find the smallest number. Then you have to do n minus 2 iterations to find the smallest number. Then you have to do n minus 3 till the time you have 2 numbers left, because that's the last minimum element finding you have to do. So I just wrote it out. N iteration plus n minus 1 plus n minus 2 plus n minus 3, so on and so forth up till 2. This series becomes sum of n natural numbers minus 1. What is the sum of n natural numbers? N into n plus 1 by 2 minus 1. And you remember, we do asymptotic analysis. In asymptotic analysis, we avoid the lower degree terms. We avoid the constant terms. So minus 1 is a constant. Think about it. If n is 10 raised to the power 5, 10 raised to the power 5 into 10 raised to the power 5 plus 1 by 2 minus 1 is equal to 10 raised to the power 5 into 10 raised to the power 5 plus 1 by 2. Can I say that? This minus 1 holds no significance. So I avoided this. I came here. Then same thing for 1 by 2 also. 10 raised to the power 5 into 10 raised to the power 5 plus 1 into 1 by 2 is equal to 10 raised to the power 5 into 10 raised to the power 5 plus 1, because this term will become 10 raised to the power 10, right? It's too huge. 1 by 2 is nothing. So we avoided 1 by 2 as well. We got to n plus 1. If you simplify n plus 1, you get n square plus n. In n square plus n again, let's say if n is 10 raised to the power 5, this will be what? 10 raised to the power 10 plus 10 raised to the power 5. Think about it. 10 raised to the power 10 plus 10 raised to the power 5 is 10 raised to the power 10 only. This is too small in front of 10 raised to the power 10. So we will avoid this lower degree term as well. And hence we get n square. And that's the worst possible case. Right? That makes the big O notation of selection sort as order of n square. How many of you guys are able to get this point? Drop a quick yes or no in the chat. Now, what will be the best possible case of selection sort? The best possible case of selection sort you might think can be, what if array is sorted? Let's say array is already sorted. For example, 1, 2, 3, 4, 5. Okay. Now, let's apply the selection sort. Initially, we know unsorted region is empty. Unsorted region is the whole array. We find the minimum element. To find the minimum element, you have to go to every element, right? Because we do not know when the input will come. We do not know where is the minimum element, right? To find the minimum element, we do not know where is the minimum element until or unless somebody tells us that your array will be sorted. If nobody tells us that the array is sorted, how do we know where is the minimum element? We have to go to every element still. So n iterations. Then we found 1. We swap 1 with 1. We are left with n minus 1 elements. Again, we do not know where is the minimum element. So you have to go to n minus 1 elements again to find the minimum element. You find the minimum element as 2, you swap 2 with 2. Then again, you try to find the minimum element among the n minus 2 elements and so on. So can you see, even if the array is sorted, you don't get much of a benefit. So even the best case of selection sort is big omega of n square, right? Is this point making sense? And on an average, let's say you had to do n by 2 times swappings or n by 5 times swapping, then also on an average also it will be order of theta of n square, right? Because on an average also that much amount of elements you will need to swap, right? So even the average case of selection sort is n square. And you can also try to figure out it like this. If the worst case is n square, if the best case is n square, on an average also it is n square, right? On an average also it is n square. That's the time complexity of selection sort. What is the space complexity of selection sort? Just like time complexity, how do we measure space complexity? We measure space complexity by the fact that what was the maximum extra space you took. You do not consider the input space in space complexity, guys. When you are given an input array, for example, this whole collection of numbers is inside an array. That's the input array, right? So you do not consider the input array in the time space complexity because that is the bare minimum to start the process, right? Do you think apart from the input array, I am taking any other extra space which will grow by this increase in the space complexity? No. No extra space I'm taking. I'm modifying the same given array. So the space complexity is constant. In the worst case, it is constant. Can I say that? And why it is constant? Because if you take an array of 100 length, then also I do not need any extra space. If you take an array of 1000 length, then also I do not need any extra space. If you take an array of 10 raised to the power 5 length, then also I do not need to take any extra space. So doesn't matter what is the length of the input, space is not changing. If space is not changing, then technically the space complexity is constant. Arun, you are taking temp variable. Let's say how many variables you will take. For completing the whole algorithm, let's say you take 20 variables. Okay, you wrote the very bad code, for example, but still you wrote the code with 20 variables. If it's a 100 length array, then also you need 20 variables. If it is a 1000 length array, then also you need 20 variables to swap and whatever you want to do. If you have 10 to the power 5 length array, then also you need 20 variables. So you take constant variables, right? Rakesh, I'm saying, like, let's say he wrote a very bad code that variables are not even deleted automatically by garbage collector. Make sense, Arun? Does that answer your question? Now let's try to code it, guys. Let's try to code it. Yes, it's the worst case. And if the worst case is constant, best case is also constant, right? Can I say that, guys? If the worst case is constant, the best case will also be constant for the space. Yes or no? You cannot take more space in the best case scenario, of course. What was our project? DSA, problem solving, right? Okay. Third was time complexity. Fourth is sorting. Okay, fourth is sorting. Selection sort. Make sense? Let's start, guys. Now, let's try to write our algorithm. Okay. What I'm going to do is I'm going to write a function. I'm going to write a function. Selection sort. It is going to take an array. Let's say this is the input array. Okay. Now, what do we have to do is we'll say for let I is equals to 0, I less than n minus 1, I plus plus. So what is this loop doing? What is this loop doing? We have the unsorted region initially from index 0. So I denotes the start of unsorted region. Okay. I denotes the start of unsorted region. Okay. Cool. Now, for every unsorted region, what do we have to do? We have to find the minimum element. So I'll write one more function. Find minimum element. We'll give the array and we will give I. What is this function going to do? What is this function going to do? This function finds out the index of the minimum element in the array from index I to n minus 1. Okay. So from index I to n minus 1, whatever is the minimum element, I will try to find out. Okay. How do we find out? We'll say let minimum index element is equals to I. So I will assume initially the first number is minimum. And then what I'm going to do is I'm going to go to every single number from I plus 1. That is from the second number. I will go to every single number. ARR.length j plus plus. And I will check if the current element at j is less than element at minimum index, I will update the minimum index to be j. Okay. That is, if the current element is smaller than the assumed minimum element, we update the assumed minimum element. Okay. And at last, we are going to return this minimum index, right? And here, what we're going to do, we're going to say let minimum index is equals to find minimum element ARR comma I. We got the minimum element. We will swap this minimum element with the first element of the unsorted region. How do we do that? We will say if minimum index is not equal to I, that means minimum element and the first element of unsorted region are different, then swap. Right? Think about it, no? If let's say you have an array like this, 1, 2, 3, 4, 5. You go and find the minimum element. You found the minimum element as 1. You do not need to swap 1 with 1 because it's already there, right? Even if you will swap, it will not hamper a lot. But still, if you can avoid the swapping, it would be good. So I'm checking. If the minimum element that I found is different than the first element of the unsorted region, then only I will swap. How do we swap? Let temp is equals to ARR at I. ARR at I is equals to ARR at minimum index. ARR at minimum index is equals to temp. That's it. We swapped, right? We swapped. And here let's calculate n. N is equals to ARR dot length. Okay. And that's it. We do not need to return anything from the selection sort because here this array is going to eventually get modified. Let's try to run our code. So I'll say const ARR is equals to 5, 4, 3, 2, 1. I'll say selection sort ARR and I'll say console.log ARR. If I run the code, can you see it sorting the whole array? It is sorting the whole array. If I take some random numbers, 9, 1, 0, 6, minus 2, 4, 8, and I run the code again, can you see it is still sorting the array? If I take even numbers, let's say 10 at the last and run it, can you see it is still sorting the array? So the overall algorithm is working absolutely fine. And if you carefully see, I less than n minus 1 means we just want to go till second last element, right? Because the last element doesn't need to be figured out that what is the minimum element. If you just have a single element, that's the minimum element, right? And that's it. That's how you write selection sort, guys. Abhijit is saying temp is extra variable used here. Abhijit, there is something called as garbage collector. The moment you will be done with the temp variable, it will destroy it. And in every iteration, you create a new temporary variable when the old variable is destroyed. Think about it like this. I give you 2 toffees. I have 2, or let's say I give you 1 toffee. When you eat that toffee completely, then I give you a new toffee. Then you eat that toffee completely, then I give you another toffee. At any point of time, what is the maximum toffees that you have? Abhijit Dinda. 1. That's constant, right? We are running till less than n, right? So that's going till n minus 1 only, Narota. If you run a loop up till less than n, that goes till n minus 1. Can I say that? Let me push this code. But are you guys able to get this point, guys? What I'm trying to do here?